fantastic and pioneering work on reinforcement learning for human-computer interaction of different sorts, especially intelligent tutoring. So let's welcome her.
Thanks everybody for coming out today. Before I get started, I just want to do a quick poll. So reinforcement learning, I'll offer you 3 options, and then I'll ask which of these resonate with you most. So the first one is that something that's related to machine learning? The second is, that's the stuff related to Q-learning, right? And the third is, are you going to cite my favorite new RL paper? Okay, so raise your hand if 1 is sort of the closest to your state of knowledge. Okay, so a few people are like, there's this thing, I've heard about it. What about 2? A lot of people in 2 and 3. All right, so I'm sorry if I don't cite it. All right, so I'm going to start off. I'll try to start from kind of the very beginning. I put this later, but as a caveat, it is unfortunately not possible to cover all of reinforcement learning in the next hour and a half or 2 hours. So apologies for sort of the huge sparsity, but I'm just going to try to highlight some of the ideas that I think are really exciting. So what is reinforcement learning? So reinforcement learning is this idea of there being an agent that's acting in the world. So the agent's going to take an action that's going to sort of interact with some environment. You can think of the agent as being a robot, or an intelligent tutoring system, or a recommender system, or something like that. And then in response, when it takes some action, it's going to get back some reward and some next state that it's then going to use as input to try to decide what the next decision it's going to make. And the idea is that this agent is going to learn through experiences, so through the actions that it takes from certain states and the rewards in the next states it observes, in order to make decisions in order to maximize some expected reward. And the key distinction for those of you that are familiar with sort of AI-style planning is that we don't know how the world works. So when I say the world here, I'll be a little more specific in a second, but I mean that we don't understand how the world transitions, how things change when we take actions, and we don't know what rewards we're going to get from taking certain actions in advance.
So is this state known to the agent, or?
Is the state known? Yes. So we assume, well, it's a little bit subtle, but in general we'll assume that there's some fully observable observation. Okay, so there's information from the world. Maybe the robot has sensors, or a customer clicks or doesn't click. So I probably don't have to argue this part to you because you guys are all here, early computer science time in the morning, but why should you care about reinforcement learning? Well, I think you should care about it for 2 reasons. The first is sort of a pure intellectual reason, which is that I think that understanding how to make decisions under uncertainty is really a core part of intelligence and autonomy. And so I think if we want to solve machine learning and we want to sort of make breakthroughs in AI, we have to think about how do agents learn to make good decisions. But the second is a more practical one, which is I think that there's an enormous number of applications that can be modeled as reinforcement learning. As Peter said, I personally think a lot about intelligent tutoring systems. I think a little bit about healthcare too. But there's robotics, there's a number of other domains where people frame this as an instance of reinforcement learning. So I thought it would make sense to just highlight why reinforcement learning is different than machine learning and AI planning. So I'm afraid I couldn't be here yesterday, so I don't know exactly what was said about optimization. But if you think about sort of standard AI planning, you can think of that as an optimization problem where we know how the world works. So we know what would happen if we take a decision, but it might be really computationally intractable to sort of enumerate all possible decisions and what might happen. So we need to be more efficient about that. So the same issue kind of comes up in reinforcement learning because we're going to be thinking about sequences of decisions made. But because we don't know how the world works, we have to tackle a whole bunch of other problems too. The first is this issue of generalization that is related to the question that just came up. Do we know what the state is? If we're acting in really large domains, things like Atari or Go, the number of states where we might have to make decisions is enormous. We have to tackle exploration, which I'll talk more about later, which is the idea of how do we actively gather the data. This is very different than standard machine learning, where our data is provided from some fixed IID distribution. Here we are going to be actively gathering the data that we receive. And the final thing that's important is that we might have a lot of delayed consequences. So it might be that the decisions that we make now have influence way, way later when we can tell whether or not they were good decisions to make. So today I'm going to sort of talk about the standard RL setting. This will be a review for some of you, and then spend some time talking about different ways that we approach exploration, as well as how do we evaluate an RL algorithm? What does it mean for an RL algorithm to be good? And then talk about sort of some of the current and future directions.
Just curious, you said
know the state of the world, or sorry, you don't know the effect of an action on the state. But in the case of Go, you surely would.
Yep. Yes. So in Go, you do know the result of a state. You don't necessarily know the distribution of the other player. And it ends up being more of a planning problem. But they have used reinforcement learning to try to tackle that enormous state space. So I'll talk briefly about that later. Yeah, that's a good point. And one thing I should say, too, is that one of the reasons I was excited to give this, this talk in this bootcamp is that reinforcement learning has been somewhat separate from the active learning community. But I think that there's a lot of overlap between the types of problems we look at. And so if anybody has connections to draw between those, I'd love to hear them, as well as any other questions. All right, and then again, just my standard caveat, I'm just going to try to outline some of the key ideas in reinforcement learning. Okay, so what's the standard setting? Most of the time, or most of the work in reinforcement learning has focused on Markov decision processes. So in a MDP, it can be specified as a tuple, where we have a set of states, a set of actions, and then we have some stochastic transition between states. So we can represent that as a dynamics model or transition model, such as T, S, A, S prime. We have some probability of reaching the next state S prime after taking action A in state S. So if you think about sort of a faulty robot, a robot might try to go forward, but maybe its wheels get stuck some of the time. So sometimes it succeeds in going forward, and sometimes it stays in the same place. We're also going to assume that it's a reward model. Going to be a little bit loose in notation here. It can either be a function of the state, or the state in action, or the state action in next state. It's almost always possible to go between any of those different definitions. So I'll try to be consistent in my notation, but know that all the algorithms basically hold for all those settings. And then we often have a discount factor, which essentially weighs how much we value immediate reward versus future reward. So are we optimizing what I'm going to eat for lunch now based on how I'm going to feel when I'm 55, or am I optimizing just for immediate reward of how good lunch tastes right now? So in this setting, we can compute a policy, which is a mapping from states to actions. That's sort of a decision policy or a strategy. And then the optimal policy is one that's going to maximize the expected discounted sum of future rewards. So it'll give us the most reward in the world. The agent is trying to obtain reward, and summed reward over time. So how do we do planning? Well, what I mean by planning, again, is just that assume that we know how the world works. So we know what the transition dynamics are, and we know what the reward model is. And all we want to do now is compute what's the optimal way to behave. So there's an equation called the Bellman equation, and it satisfies the following structure. So we can say that the optimal future discounted set of rewards we'll get from starting in state S and taking action A is the immediate reward we get plus the discounted sum of future rewards. And this equation exactly holds for when we have the optimal state action values. Now you can notice here that we are using the Markov assumption. The Markov assumption is that the current state is sufficient to make future decisions and sufficient to encode the reward. And so we don't have to think about the full history of all the past states that we were in. We can just think about the current state we're in and where we could be next. And that's encoded in the transition model. Now this might sound like sort of a restrictive assumption, but you can always kind of cheat and you can put the full history into your state space. So it's a very expressive model. It's just that if you put the full history of previous actions and states into your sort of state space, then you can get very, very large domains. All right, so we can use the Bellman equation as an update expression, where we can start off and we can initialize our Q function to be 0 everywhere, and then we can iteratively update it. So we can sort of do these Bellman backups, where you can think of this as saying, what's the reward I'm going to get if I get to act for a single time step? And then you can use that to bootstrap to figure out how much reward you would get if you got to take one action and then stop, or 2 actions and then stop. And each point you're using the previous Q function to sort of represent how much reward you'd get for the remaining time steps. So the nice thing about doing this is that the Bellman update is a contraction operator, so this will converge, at least in the tabular setting. So what I mean by tabular setting is imagine you could enumerate all of the states and enumerate all of the actions, and you literally just have a table where you keep track of all of the Q values. So in that setting, the Bellman operator is a contraction, and so you can show this is guaranteed to converge. Another approach is to do policy iteration, which means basically you maintain an estimate of what the policy value is right now, and then you try to improve the policy over time. Now, just note here that at any point, if you have a Q function, that is sufficient to extract a value and also to extract a policy, because you can take the argmax of the Q value to figure out how you should act in a state. So there's sort of three different ways people often think about trying to do planning in MDPs and also often learning, which is we can think of trying to explicitly learn the models. So how the world works, the dynamics model and the reward model. We can think of directly trying to learn the state action value function, and we can think about learning the policy directly. So there's this nice figure by David Silver where he sort of says you can break all of reinforcement learning into mostly these three different camps. And then you have intersection, there are a number of algorithms that combine different approaches. So actually our critic methods can combine sort of having a value function and a policy. So I'll talk about some of the standard ways to do this. So what's model-based RL?
Question?
Yep.
So is this just a classification of algorithms, or also there's some different information being collected about the world?
This is right now just a classification of algorithms. So model-based reinforcement learning is essentially the idea that we're going to use our experience. So experience here again means I'm in a state, I take an action, and I observe a reward in the next state. So I'm going to take all of those tuples of my experience, and I'm going to use it to estimate a model of how the world works. So for example, you could take all of that data and do maximum likelihood estimation to get a model of the dynamics and the reward. And once you have that model, you could do Bellman updating, like value iteration or policy iteration, to compute a Q function and to compute a policy. So having the model is sufficient for us to compute the state action values and is sufficient for us to compute a policy. So why would we want to do this? Well, the nice thing about this is that it uses data pretty efficiently. So we're going to take our data, and then we're going to estimate our models from it. But once we have those models, you can think of them as a simulator. So once you have these simulators, you can estimate the value of any policy. That's not totally true. It depends a little bit on your data. But essentially, you can think of it as you get a simulator, and now you can estimate the value of any policy. The problem is it can be pretty computationally expensive. So an alternative approach, which is computationally much more feasible, is Q-learning. So in Q-learning, we're not going to learn a model of how the world works. We're just going to sort of implicitly take into account how the world works when we're computing the Q functions. So the idea in this scenario is we're going to initiate the Q functions for all state action pairs. And then whenever we observe a transition, so when our agent is in a state, it takes an action, goes to a next state, and it sees a reward, we're going to compute what's called the TD error. So the TD error here is basically the difference between your current estimate of the Q function and your new update of the Q function. So you just saw a reward, and you can use that to compute one estimate of the future reward by combining that reward plus the discounted expected sum of the future rewards minus your current estimate. This sort of tells you what's the difference between my current estimate of the Q function and what my new information might suggest the Q function should be. Once you have that, you can update your current estimate of the state action pair. Now this should sound slightly inefficient because we're only going to update one state action pair after every data point in the initial way. So remember, in the model-based approach, we would compute entirely new, potentially, we could compute entirely new models after every new data point, and then update the Q value for every single state action pair. In Q-learning, we're only going to update the Q function for one state action pair, the state and the action that we just took. Yep.
What is the A in the equation of TD error?
It's the action that we actually took in the world, and then this A prime.
The last one. The last.
This one?
No, the next.
Oh, sorry, that should be
the
AT.
next one, yeah.
AT.
80, okay.
Yeah, sorry. So that should be the same action as there. Yeah. So this is just our current estimate of the Q value for STAT, and then our new updated one. So this is clearly, yep.
Sorry, I'm confused. Something switched in the meantime. So now we don't know the it's not the Markov decision process anymore, right? Like, so
It's still an MDP. We just don't know how it works.
Oh, so we don't know the transitions.
We don't know the transitions, and we don't know the reward function. We can only observe them from.
But like here you like sort of try to find the maximizer over all possible actions. So you know the Q, like this Q function for a particular state, or so what do you know and what do you don't know again?
So we're going to initialize. We're going to sort of make up an estimate of what the Q function should be at the beginning. So we're going to initialize it, say, to 0 or to Rmax. It actually matters how you initialize it, but imagine you just initialize it to a constant. And then what Q-learning is doing, you can think of it as slowly moving you towards the true Q estimate. It's going to do it quite slowly here because you're only updating the current state and the action every time step. Okay, so that's computationally, yep.
If it only relies on the current data, the current transition or whatever, how is it explorative?
It's a great question. We've not got to exploration at all right now. So I'm not talking about how we pick the action. Yeah, I'm just saying that if you pick the action, this is what we could do.
So with the model-based learning, it sounds like you're sort of like iteratively approximating a whole bunch of things and then sort of, approximating more things on top of that. So does that tend to be like robust if like, you sort of pick up like sort of noisy like model and things, and then on top of that you're estimating like your Q function, and on top of that you're estimating your policy. So does model free tend to be more robust, or?
It's a great question. So probably everybody heard that, but the question is if the model, we're getting compounded errors here. If we're estimating a model and there's model approximation, and then we're using it to compute a Q function and then using it to extract a policy, couldn't those compound? And the answer is yes. And I'll talk a little bit more about the theoretical guarantees. We can show if the models are close, that our Q functions are close in a bounded way, but it will compound. Direct Q learning often actually is worse in terms of some of that compounding. And I don't know if I have a slide on that here, but I'm happy to talk about that. Okay, so this is computationally cheap, but it only propagates the experience one step. But for those of you that are familiar with some of the recent results coming out of DeepMind, there are kind of ways to get around that. Now, they require computation, but so there's sort of no free lunch, but you could either do something like this where you're only updating the current state in action. That means you're not propagating information very much. So I guess as sort of an example for why that might be a problem, let's see. So imagine that you're trying to walk down a long corridor and figure out kind of the best way to get to some destination. Q learning, let's say when you finally get to a goal or really high reward state, would only update the state action value of that current state. But what model-based would do is it would compute that new updated reward for that final state, and then it would propagate that information all the way back. Because when you do the MDP planning, you would now be using the new reward models. If anybody has a question about that, just let me know, because it's actually a really important idea that you could either use all your information and recompute from scratch your sort of your Q function using the resulting models, or you could just do local updates where you're sort of locally updating your Q function everywhere, which is computationally cheap, but not particularly sample efficient. Yeah.
So probably you get to this, but if your state space is big, it's going to be exceptionally slow, right?
For model-based?
For this, right?
For both, yeah. So model-based is even worse. But for Q learning, this could be pretty bad. It's not. It's definitely better than model-based. But yes, it depends on how we're doing these updates. And then we want to do generalization, and I'll talk a bit about that later. So we wouldn't actually want to represent this with a table.
I guess I'm confused about the idea that model-based would always be slower. It seems like if you had some tricks to inference efficiently in that setting, that could be much faster than Q learning.
You mean computationally slower?
Yeah.
Yeah, so I think it depends a little bit. So if you re-estimate your models from scratch and you recompute Q from scratch, it's definitely slower. If you do something smarter where you're kind of locally updating your maximum likelihood, and then you're sort of doing a warm start where you start with your Q function from last time, it can be much better. It can be much faster than starting from scratch. So this is only going to propagate experience one step, but replay can help this. Replay means basically sort of replay your experience over and over again. Now that's going to be more computation, sort of like reliving that sample that you just observed, and it can allow you to sort of propagate information, but then there's more computation. And then a third really common approach is policy search. So the idea now is we're going to throw out the Q function. Well, sort of indirectly, we're gonna throw this out, that we still have to estimate the value of the policy, but we're not gonna think about models at all. We're just gonna assume that there's some sort of function space that describes the value of a policy, and we're gonna do gradient descent on that to try to find the argmax, the best policy. I'm not gonna talk very much about this today, but I think that Sergey Levine will likely talk a lot about this afternoon. All right, so one of the questions that just came up was, well, what about, how do we act? What about exploration? I haven't talked at all about how we're selecting the actions that we're experiencing in the world. So first of all, does it matter? What, do we even have to think hard about this? So again, remember, we're going to start off not knowing how the world works. And then we're going to get some data, and we could use it to sort of estimate these Q values or these models or these policies. But the problem is that if we don't have very much data, and possibly even if we have a lot of data, that data either might be misleading or we haven't seen everything yet. So we've only sort of explored a little bit of the state space, or maybe we were just unlucky and we got a series of sort of unlikely transitions. So it's like if every time you go to the airport, TSA is backed up. It's probably not always backed up, but if you use that to build a model, then you might assume that whenever you go there, it always takes 3 hours to get through TSA, because you've only had a limited number of experiences. So the idea is that if we have these sort of stochastic models, that if you only have a finite number of samples, those samples could be misleading if you use them to compute the estimate of how the world works. And so we might want to try things that we don't think are optimal yet. So given some data, I said we could compute, these Q values, and from the Q values we could extract a policy. And this would say, go to the airport 3 hours early. But you might want to try going to the airport half an hour early, and then see how that goes. I'm going to talk more about that particular example later. But so the idea here is that you can try things that either you've never tried or that you haven't tried very much to learn better about how the world works. But eventually you want to gather high reward. So eventually you want to be exploiting the knowledge that you have about how the world works in order to gather high reward. And so this is the tension. The tension is that the agent itself is responsible for collecting the data it uses to then estimate how the world works. And so it has to think carefully about how to gather that data so that it can actually learn to achieve high reward over the long term. So I think probably if I had to summarize kind of what some of the key ideas are in how we should balance exploration versus exploitation, it would come down to sort of the following 4 ideas. That you can act greedily mostly, sometimes randomly. You can be optimistic in the face of uncertainty, or we can be Bayesian. And at a high level sort of summarizes a number of the main approaches. And to explain them, I'm going to first go to a simpler model, which I think illustrates these ideas nicely, which is a multi-armed bandit. So raise your hand if you're familiar with multi-armed bandits. Okay, so most people are, right? So I'll go through this quickly. So in a multi-armed bandit, it's like reinforcement learning, but there's no state, at least in the simplest version. So you just have a set of arms, or you can think of these as actions. Arms are actions. And then you have an unknown probability distribution of a reward for pulling a certain arm, for taking a particular action. So at each time step, you select an arm, and you get a reward that's sampled from that underlying unknown distribution. And your goal, just like in RL, is to maximize your cumulative reward over T pools, where T could go to infinity. Now, if you knew what this was, if you knew what the reward distributions were, this would be a simple problem. You just select the arm with the highest mean. So if you knew what all the distributions over the rewards were, you just pick whichever arm has the highest average reward, and then you would pull that arm always. The problem is that we don't know what that is. So one thing we could do is e-greedy exploration. And the idea in this case is that we use our old data, all the experiences we've had so far of pulling an arm and getting some reward back, to estimate the mean reward for each arm. So this is just counting. We just take all of the times that we've got rewards from that arm and then divide by the number of times we've pulled it. And that'll give us some estimate. And then with probability 1 minus epsilon, we're going to select the best arm so far. The best arm according to our estimated means. And then with probability epsilon, we'll select a random arm. This is a super easy strategy. It just says, most of the time be greedy with respect to the information you have about sort of what the reward distribution is in the world, but sometimes be random. To show that there's some formal guarantees for this particular approach. Okay, so this is the first approach. The second idea is optimism under uncertainty. All right, so again, this is a very similar idea. Given the observations we've had so far, we'll again compute the mean reward. But now, instead of just using that mean reward to act, we're going to compute an upper confidence bound on what that reward could be by using concentration inequalities. So for example, if we use Hofting inequality, then we can get an upper bound on what the mean is of an arm by our empirical mean so far, plus a term that looks like this. So this log t here is going to be the number of times we've pulled an arm. You can think of this as accounting for sort of union bounding over the probability of making sure these concentration inequalities hold, divided by the number of times we pull that arm. So intuitively, what will this do? It means that if we haven't pulled an arm very much, then we're going to have a really large bound here. And so that's going to drive us towards picking it. Yeah.
Are you making an assumption that there's an upper bound on the rewards?
So this has to assume that, that the rewards are bounded.
Do you start initially with each one pulled once or something like that? Because otherwise...
It could be unbounded. At the beginning, yes, you'll always will put, if the action space is infinite or continuous, that's tricky, but if the action space is finite, then yes, you'd pull everything once. Though I should talk about that more for Go, because it turns out if you've got a huge action space, that starts to be very important.
T is the total number of rounds that you have?
T is the total number of times you've pulled any arm. Again, you can think of that as kind of union bounding over the concentration inequalities to make sure these all hold simultaneously. So this is nice. Why is this a reasonable thing to do? Okay, well, the intuition is either the arm that you pull is either really the best arm, in which case you're going to get high reward, or it's not a good arm, and you'll get information that allows you to revise that estimate. So if this upper bound really is representing that this is a great arm, then you're going to get large reward, and that's good because you want to be getting large reward. And if it's a bad arm, then you're going to get a new reward that's going to update your expected reward, and this is going to increase by 1. And so your confidence bounds are getting tighter over time, and you're getting more accurate estimates of the mean. So that's why optimism under uncertainty is sort of this nice principle. If you think about being pessimistic under uncertainty, which a number of humans probably are, you're not going to necessarily get any information that allows you to revise your belief. Because if the world really is bad, you'll learn that, but you won't have tried out things that could have been really good. So this is letting you try things that could be really good, and either they are really good or they're not, and then you'll learn to stop doing them.
So a lot of people react under punishment. Is there a model that works under punishments instead?
Under punishments? I don't know. That would be cool to look at. Yeah. So I think this definitely is a very logical approach to it.
Wait, punishment is just negative reward, right? Is there?
You mean as a cost function?
Well, maybe, but I think people react differently to a punishment versus...
Yeah, so you can flip all of this. You can flip it and make cost instead of reward, but this is not modeling how people would react to that, because it wouldn't be symmetrical.
Yeah, of course, that's psychology.
Yeah. All right, so this is the second approach. Notice that this is not making any assumptions outside of the fact that rewards are bounded. So I'm not assuming anything about the distribution of the rewards, except for that I have bounded rewards, and that everything is IID. So an alternative approach is we could be Bayesian, and we could think about having distributions over worlds. And when I say distributions over worlds, I'm going to mean distributions over the parameters that govern the reward distribution for bandits. So we could encode a prior distribution over the rewards, and then we could update that posterior every time we pull an arm and get some observation back, some reward back. So now we can just maintain this sort of posterior distribution over what our reward distributions could be for each arm based on our prior evidence. And once we have that posterior, we can use it to guide exploration. So one approach for doing that is known as probability matching. The idea in probability matching is that you could choose an arm with the probability that it's the optimal action. And now you can represent that probability because you have a distribution over what the rewards could be for each arm. So if we just write it like this, then we're saying that the probability we're going to select A, given our history of arms we've pulled and rewards we've seen, is the probability that the mean of that arm is greater than the mean of any other arm. Now the problem with this formulation is that it can be hard to compute analytically, but the sort of elegant idea that Thompson sampling encodes is that in fact we can just compute this by sampling. So again, if we rewrite this equation here, we can think of instead of this as being sort of the expected, the expectation that A is the argmax, given the probability distribution over reward functions. This is a really nice, elegant idea. So the idea is that we're going to maintain our full posterior over what the reward distributions could be, and then we can sample from that. So we can sample a particular instantiation of a reward for each of the different arms, and then we just pick whichever arm has the highest reward in our sample. So we don't have to directly compute this. We just have to always be able to update our posterior. And so then we can just compute the mean given the reward distribution we've sampled and act accordingly. So as long as it's pretty cheap to represent your posterior, this is a really nice computationally efficient approach.
Sorry, so under what conditions can you represent the posterior?
It just depends on the domain, yes. So like, I mean, you could do something like Bernoulli beta, and then it's nice, everything's conjugate. But if you've got much more complicated distributions, like really large sort of factored action spaces, et cetera, it could start to be complicated to compute the posterior.
So what equation should the distribution satisfy?
So what we're doing here is we have some distribution over the reward function. So this could be, let's imagine that our arms, each of them is just a Bernoulli. So, and then what we have is a beta prior over what that parameter is. So then every time, we pull an arm, we're either going to get a 1 or a 0, and then we can update what our posterior is over that Bernoulli parameter. And then in order to act, what we do is we sample that Bernoulli parameter for each of the arms, and then we pick whichever arm has the highest one. And then we pull that arm, we get a 1 or a 0, and then we update our beta prior. So that'd be somewhere where it would be really cheap to compute. That's a very simple model of reward distribution, so it could be much more complicated than that. But
So this procedure can be proven to converge as you get more and more data. The posterior will concentrate on the one with the...
Yes. Yeah, and I'll talk about more sort of what guarantees this allows us to have, but yes. Yeah, so this will converge.
Does it have guarantees even if we do not assume that the world is a better distribution? Like, even if we assume that we are wrong, what kind of guarantees you have?
Can you have if your prior is wrong?
Prior,
yeah. So in general, nothing. So we're going to end up with sort of Bayesian regret style guarantees. There is work on sort of pack Bayesian analysis where we can try to be a little bit more robust to the prior choice, but in general, that's a big limitation. Yeah. So if you really do, and you can try to make your prior as agnostic as possible or uninformative, but then it's maybe not as helpful. Okay, so this is one thing we could do. This is probability matching. What's something else we could do? Well, what might we really want to do? I said before that what we want to do is we want to get the most amount of reward we could ever achieve, for our agent. So if we have a prior distribution over the parameters, and let's say we know how many steps we're going to get to make decisions for. So I'm going to get to be in the casino for 8 steps. I get to pull the arms 8 times. What you could imagine doing, if this was computationally tractable, is to pull the arm to maximize the cumulative expected reward over all 8 steps, given your prior. So this is going to directly reason about the value of exploration versus exploitation. So it's going to sort of think hard, and it's going to say not which arm should I pick sort of immediately, but what arm should I select so that over the next 8 steps, if I act optimally for this step and then optimally for all future steps, is going to give me the maximum expected return. And to some extent, this is the best we could ever hope to do. Now, this sort of only applies in the Bayesian setting, but essentially this is going to optimally balance exploration versus exploitation. And I think that sort of how we can do this is a super elegant idea that is not yet computationally tractable. So another way we could think of this is what we're essentially going to be doing here is we're going to be transforming a learning problem into a planning problem. So this is sort of learning as planning. The idea is that we can think of this really as a sequential decision-making problem where our hidden state is the parameters. So the parameters of our arms. This is a really cool idea. So here are the parameters of our arms. If we go back to the Bernoulli beta, it's sort of what our Bernoulli parameters are. And these are static. We just don't know what they are. So there's some reward distribution for each of the different arms. We just don't know what it is. And we're going to assume those parameters are static. They don't change when we pull the arms. We just don't know what they are. And we get to observe them sort of indirectly when we pull the arms. So we have this sort of hidden latent state, which is our arm reward distribution parameters. And that's static. And then our actions are our arms. And then our observations are the rewards we get from pulling the arms. And then our posterior, which we can also think of as a belief state for those of you familiar with partially observable MDPs, is a probability distribution of our arm parameters, just like what we were doing with posterior matching. The difference is how we use it. So the cool thing about this is this actually forms a partially observable Markov decision process with a set of static hidden states, which is the parameters. And so if we could compute the optimal policy for that POMDP, then that would actually yield the Bayes optimal solution for bandit learning. So that would directly maximize our expected discounted sum of future rewards. So that would be awesome, right? Like then we could exactly think about how much benefit is there to sort of select this arm that might or might not be optimal, given the remaining time steps I have and the information I might get. So just as an example of where you might want to do something different based on the number of time steps you have left, if you know you're going to get to, select between a set of arms for a very long time period, you might still do some exploration to see whether or not an arm is good or bad. But if you only have one time step left to make a decision, you're going to select the arm that has the highest mean, highest empirical mean. You make different decisions based on sort of the amount of remaining steps you have to act in the world and whether or not you could benefit from the information you might learn. Let's think directly about that. Yeah.
What's the relation with the Gittins index?
Exactly the Gittins index. Yes. Yeah. So the Gittins index is exactly exactly what we're doing here. We're doing sort of exact optimal computation of what this policy is. The problem is, just like viewing this as in the POMDP framework, that's often computationally intractable to do because the hidden state here is continuous. It's the actual parameter. So it's the Bernoulli parameter, or it's whatever way we're parameterizing our distribution, which will generally be with continuous valued parameters. And so doing this planning problem, doing POMDP planning or computing the Gittins index is generally computationally intractable. So if we can solve it, this would be great, but often this is very hard to do.
In the case where you have several arms and the prior is some sort of a simple conjugate, is the problem solvable?
The problem is, so you can, let's see if I've got it on the next slide. So the problem is solving the POMDP. So we can use approximate techniques for solving the POMDP, like Monte Carlo tree search, and then we can get an approximate solution to that. So there, the inference and the updating isn't so much of the problem. The problem is sort of, you've got this branching factor of all the actions you could take, all the arms you could take at each step, and all the observations you could get back, and then you kind of have to think about doing that up to the horizon. So that would be sort of a tree that's the size of the actions and the size of the observation space to the h. And so we could use stuff like sparse sampling or Monte Carlo tree search to try to approximate that. And people have, but that's why it's still computationally challenging. One of the downsides is that typically a lot of the ways that we try to compute the Bayes optimal solution means that we don't have any guarantees on the resulting quality. So I think one of the challenges is that I think it's a really beautiful objective for us to be aiming for, but it might be that the way we compute it, like the algorithms are so approximate that we lose any guarantees on the resulting solution.
So when you build as a POMDP like this, is it obvious that things factor into, an index policy where you have to compute something complex for each arm, but they get combined in an easy way?
I don't think so. I mean, I guess I also think of this as extrapolating directly to the RL case, and I haven't thought about it as easily as directly for the Bandit case. It's an interesting question. I think that the posterior should factor out, but I think if we view it as kind of this branching tree, the sort of the index structure wouldn't be immediately apparent. So these are kind of, to me, the sort of key ideas that we often use in exploration. We can either do some sort of E-greedy, or we can be optimistic in the face of uncertainty, or we can be Bayesian and then try to leverage that information either to sort of sample a world and act accordingly, as if that sample was the real world, or where we try to reason directly about the full distribution over our parameters and then leverage that in order to make decisions. So this was all for the Bandit setting. It turns out that for reinforcement learning, almost the same. So the challenge is that there, we have to think about the long delayed reward. So generally, we're going to be operating directly with the Q functions instead of the reward function. So for example, acting greedily mostly, or E-greedy, means that we're going to compute the Q values given our prior experience. And that could either be done using something model-free like Q-learning, or it could be done using something model-based. And then given our current state, either with probably 1 minus epsilon, we're going to be greedy with respect to our current Q function, or else we're going to select an action at random. If we think about being optimistic in the face of uncertainty, we essentially want to compute upper confidence bounds on the Q functions. And then select the action that is the argmax of those upper confidence bounds on the Q function. There are lots of different ways to do that. I'll talk about sort of a couple different approaches for computing those upper confidence bounds, and there's definitely differences depending on the techniques we use in terms of how tight they are. But that's essentially the idea. We're just going to directly compute sort of an optimistic estimate of what the Q function is and then act accordingly. And then this part gets even more complicated, So if we want to have the distribution over worlds, now we're going to be representing the distribution over the transition model as well as the reward model. And so that's typically, particularly here, where we get very approximate solutions if we try to do Bayes optimal RL. In cases of posterior sampling, we can actually get some very nice results in that situation. Again, assuming that our prior and our posterior are pretty efficient to compute. Okay, so that's a couple of the techniques that we could use to do exploration. A natural question is how good they are. How good are they? Which of these should we pick, and does it depend on what the criteria that you care about? So I'm going to mostly talk about performance of RL algorithms. And when I say performance, I'm mostly going to be thinking about the rewards that we get back, or the amount of data that we need to get back in your optimal policy. That is not at all the only criteria that people care about. I would argue that a lot of the 90s, not all, depended on the community, but there's certainly a number of RL researchers that have been very, very focused on computational efficiency, which I think is also a very valid criteria to look at. But I'm not going to talk very much about that, because I want to focus more on just what is the quality of these algorithms that we're going to be looking at, and how would we compare amongst different RL algorithms. So the first two are somewhat straightforward. Empirical is empirical. We're going to do experiments on particular domains. We're going to see how well they work, and then we can compare. I laugh slightly because even I'm sort of being cavalier about that, but that's very important. And we know often that in practice, some of the algorithms that have better theoretical guarantees in practice don't do as well empirically, either because they can't scale up, or because if you tune the constants of some of these other algorithms, then you end up getting much better empirical performance. So empirical performance is very important, but I think on the other hand, to me, I think the theoretical guarantees are also very important because they give us a notion of generalization beyond the particular domains that we're going to look at.
The sort of empirical measures, do they typically just look at the total reward?
It's a great question. So in terms of what we measure when we measure empirical performance, I feel like there's a number. It's often sort of total reward, cumulative reward. Another can often be jumpstart performance, like how quickly do you start performing well. That's particularly important in like transfer learning type settings. Sometimes we look at average reward over time, and sometimes we look at asymptotic performance.
And in terms of like what it means to perform well, is that sort of with respect to, because so finding the very best arm or the very best policy might just be
totally intractable. Yes.
Completely out of the question. So
Yes.
what's a reasonable?
Yeah. So I'll talk about that a little bit. I'll talk about that more in best in class. At the beginning, I'll be talking about this relative to assuming that the true optimal policy is realizable, and then at the end, I'll talk a little bit about what if that's not the case. Like maybe we'll have an approximation error. So empirical, we look at how well we do on Atari, and we compare normally to other baselines. Convergence is another very important property. The convergence is just saying, as we do learning over time, are we going to converge to a single estimate of the Q function? So if you keep making decisions in your domain, let's think about reinforcement learning, and you keep gathering reward, eventually is it going to become stable? Are you going to sort of have a single estimate of the Q function in all of the states and actions? And that's actually not trivial, because depending on how we're representing the domain, that's not always the case. So we could end up oscillating, and that was something that was noticed in the 90s. And so convergence itself is not always trivial, and where you will converge to, even if you're guaranteed to converge, it may just be a local optima. But I'm going to focus on the rest of these for now, which is starting with asymptotic optimality, which the idea in asymptotic optimality is that eventually we'll converge to the optimal policy. So again, I'm assuming realizability here, that there's an optimal policy, and we can represent that using the state and action space that we have. And if we are greedy in the limit of infinite exploration, and what that means is that if we think of something like E greedy, then we sort of decay our epsilon parameter that we're using to make a random decision instead of the sort of greedy optimal decision given our data so far. So if we continue to explore forever, but we kind of decay the rate that we're doing that exploration, then we can guarantee that Q-learning converges to Q star. So that could be incredibly long, but at least it's sort of a nice sanity check, saying eventually we're going to converge to the optimal performance. That's true also for the model-based approach. So it's been known for, I guess, about 2 decades.
This is not uniform over, like, the rate depends.
It's not telling at all about the rate. This is just, yes, this is just saying that we will converge eventually in the limit. Yeah, it's not saying that it'll happen at all quickly. Okay, so these are sort of some of the first guarantees that came out about sort of what is the performance that we might get in reinforcement learning. It's not very satisfying, particularly if we're not going to act forever. I think it's sort of a reasonable guarantee, but I think we'd like something stronger. So one notion that's stronger is probably approximately correct RL. This is also strongly related to the knows what it knows framework from Michael Littman's group that later came out. So the idea is that we're going to think about probably approximately correct reinforcement learning. Some of you guys are probably familiar with that from supervised learning. But we're going to think about it for reinforcement learning, and the way we're going to define it as follows. So we're going to say an algorithm, a reinforcement learning algorithm, is POMDP if on all but n steps, where n is some finite number, the algorithm is near optimal in the decisions it makes. So it's saying that we might make a bounded number of mistakes. We might sort of screw up and make really dumb decisions n times. But aside from that, we're going to make decisions that are near optimal, that are epsilon close to optimal. And we want that the number of times where we make mistakes to be a polynomial function of essentially the domain parameters. The size of the state, action space, 1 over epsilon, 1 over delta, 1 over 1 minus gamma. And we're only going to be able to guarantee this with high probability. So with probability at least 1 minus delta. The idea for this is that because these are probabilistic domains, there's always some chance that we might get super unlucky and see a sort of a series of very unlikely data points. And so in that situation, we might end up learning a bad policy. But in the general case, we expect with high probability that we're going to be able to make very good decisions.
So A here is both the algorithm and the set of...
Yes, sorry, I should have clarified. So A here is the size of the action space. This is the size of the state space, this is the size of the action space. AT is like what the policy is for the current algorithm at that time point.
So I have 2 questions. First of all, what is gamma? And second of all, can it be log of 1 over delta instead of just 1 over delta?
Often it ends up being a log term in terms of 1 over delta. Yeah. So, and then gamma here is the discount factor. So you can think of this as basically being the horizon, the number of decisions we make. So how would we show something as PAC? Well, first, this is sort of a framework that was come up by Michael Littman's group in 2006 that we can use to characterize whether a number of different reinforcement learning algorithms are PAC. And the notion is as follows. So first of all, we're going to define a reinforcement learning algorithm as being greedy if what it does is it maintains a Q function. This may not be the real Q function. It just has some estimate of the state action values in its head. And the way it acts actions is to take the argmax over that Q function. This is just saying how it behaves. So if I give it a Q function, it's going to pick the action that argmaxes the Q function for the current state. So this is kind of one of the first key ideas for PAC algorithms. The idea is that we're going to define sort of a couple different classes or a couple different instances of MDPs that are related in some way to the true MDP. So let's imagine that we have a known MDP MK. That's going to be related in some way to the real MDP M that is unknown. So it takes as input some Q function. Again, I'm not saying where that comes from and if that's good or bad, but it takes as input a Q function. And then it also takes in a set of known state action pairs. I haven't told you how we define that, but then what it does is given that set of state action pairs and that Q function, if a state action pair is known, then we're going to define the transition and reward model using the real MDP. So it's like an oracle gives us the real dynamics parameters and the real reward parameters. But if a state action pair is not known, we're going to use a self loop. So we're going to define the transition dynamics as if we always go back to the same state we started in. And we're going to set the reward to the input Q. So in particular, typically what we end up doing is we end up making that input Q a really, really large value, like the highest possible value we could ever expect in this domain. What will that do? That means if we were to solve how to act in the known MDP, we would end up taking actions that drive us towards unknown state action pairs. So if I make the Q function here, like a really, really large reward, higher than anything I could ever experience, then if I then computed a policy for my known MDP, I would be driven towards parts of the domain that are unknown. Because it would hypothesize in its head that those are places where we would get a large amount of reward. So it's just like the optimism under uncertainty idea. We're going to sort of imagine that things that are unknown are places that they could be really good. So if we have this form of algorithm, which takes in as these parameters epsilon and delta, and it's greedy, which means that it maintains an estimate of q, and then it always acts greedily with respect to it. Let's imagine that we have the following properties of that algorithm. So the first is accuracy, and what this says is that the real value in the value in the known MDP of ST versus the value we have of our current policy is less than or equal to epsilon. So this is accuracy. I'll talk about how we could guarantee all of these. The second is optimism. The estimated Q function we have is always at least epsilon, at least the optimal Q function minus epsilon, and that we have bounded learning complexity, which means the number of times we update our Q function and the number of times we can visit an unknown state action pair is finite. And in particular, going to be bounded by some constant. And I'll talk about what those parameters should be. So if we can satisfy these conditions, then the resulting algorithm is PAC-MDP, PAC-RL. So the idea behind this is that you can kind of define the horizon on which you're acting into episodes. And during each episode, either you're not going to update your Q function at all, you're not going to reach a state action pair that's unknown. And if you do that, then you can prove that you're going to act near optimally. So if your agent is wandering around in the domain and you're not changing your Q function and you don't visit any state action pair that's unknown, then you're going to be acting near optimally. Or you are going to update your Q function or visit an unknown state action pair. Those are the only two sets of events that could happen. And if we use some threshold to decide when a state action pair becomes known, so in the simplest case, we just say the state action pair becomes known when we reach some threshold, say 10 million, or whatever. We'll talk about exactly what the number should be. But when we reach some threshold, we're going to set it to be known. And by the pigeonhole principle, we can ensure that we can only visit a state action pair a finite number of times till we reach that threshold. So that means the second set of events is bounded. So either we're going to be acting near optimally, or we're either going to be visiting an unknown state action pair or updating the Q function, and those events are bounded. And that's what's going to give us our N, the number of mistakes we could make. And intuitively, what you can think of here is that if we visit a state action pair enough, then we're going to get a pretty good estimate of how well it works. So if we visit a state action pair 10 million times, then we're going to have a pretty good estimate of its transition model and its reward function. So how can we ensure sort of these different conditions, accuracy? So this relates back to one of the questions before. If we have an approximate model, how does that relate to the true model, and what does that mean in terms of the errors that might compound? So the simulation lemma says that if two MDPs have close, as measured in like a max norm parameters, then the value of their policy will be close. It'll be further than the parameters are, but it'll still be boundedly close. And so you can, since we know how many samples we need to get close parameters relative to the true MDP, we can use this to bound how many samples we need in order to get sort of a very accurate estimate of the value function. So we can propagate the errors in the model into the errors in the value function. So the second thing is optimism, which is making sure that we have an optimistic estimate of the Q function. And this, again, we can ensure by combining the simulation lemma with the fact that we're going to use an optimistic estimate of the rewards for all the unknown state action pairs. Which means when we compute our Q function, we're basically trying to use sort of a good estimate of all of the known state action pairs and a really optimistic estimate of all the unknown state action pairs, which means the resulting Q function is optimistic with respect to the true optimal level. So these are sort of the main tools that we can use to show that an algorithm is PAC. I think that there's sort of a number of different positives and negative aspects towards taking this particular approach. The positives is that we get a finite sample complexity. So we're really bounding the total number of mistakes that we make ever with high probability. So we're not saying that asymptotically we're going to get good performance. We're saying that on all but a certain number of steps, we're going to be making good decisions. The downside is that if we try to implement this, normally we end up exploring for way, way longer than actually what is necessary. So I think it's always helpful to instantiate bounds. So these were some of the early pack bounds. This is the number of non-near optimal steps, so the number of times we might make bad decisions. This is the size of the state space, this is the size of the action space. This is epsilon, this is sort of how close to optimal we want to be, and this is basically the horizon. So if we think of a really, really tiny domain, like 10 states, 10 actions, an epsilon of 0.1, then we would get something like 10 to the 12th samples. And this is an absolutely tiny domain. For those of you that are familiar, this would be something like grid world. So this seems absolutely crazy, right? Like there's no way we should need 10 to the 12 samples in order to figure out how to act in the domain. So you might just wonder whether or not these bounds are sort of horribly loose. We are starting to make some progress towards getting near tight pack bounds now. So we've shown that for the episodic case, we can get much tighter. These are basically tied up to a factor of s. This is s squared a h cubed. And then if the domain is non-stationary, so that means your dynamics could change at every time step, but you only have sort of h time steps before you reset, then these are tight up to factor h. Sorry, that should be an h to the 4, up to a factor of h.
So can you remind what is episodic?
Great question. So episodic here means that you act for h steps and then you reset. So you could just act forever. And what this says is that every h steps, you reset back to some starting distribution of states. And in some domains, that's not very reasonable. I think in a lot of, there are a lot of domains where it is. So in the case of my sort of situation, it's like you teach a student first semester, and then you teach another student first semester. And so you don't sort of have an unbounded infinite horizon. So I think in a lot of cases, there are sort of a natural horizon of the task, and then you reset it and you repeat.
So I have, again, two questions as usual. So one is, why is the upper bound s and lower bound described? Maybe I don't understand upper and lower bound.
Yeah, so this one should be h to the 4 up here. So up here. So this one has a worse factor of s, and this is assuming stationary dynamics.
Yeah, but the lower bound is bigger than the upper bound.
This one is lower.
So it's the other way
Oh, sorry. Yes, I have a flip of, so it should be upper bound on the left and lower bound on the right.
Okay. And then the other question is, where's delta here?
This is being hidden in the log terms. I'm using an O tilde. So you definitely still have delta. We normally have a log 1 over delta.
So is this a different analysis for the same algorithm, or you actually gave a new algorithm?
Both. There are different algorithms, and it's a different analysis. So the key way, so I'll update these in the resulting slides. The key way that we ended up getting things that are much tighter is two. One is that we refined the notion of knownness, and this is based on some work from Tor Latimer and Marcus Hutter. So in the original definition of knownness, you sort of have these thresholds where you say either something is known or unknown, and maybe have a number of samples until something becomes known. Sort of slight looseness. There's sort of, it's more subtle than that, but that's sort of the basic idea. So if you get, 10,000 samples, then you declare that you know the state action pair and you have a good model of it. Well, in reality, you probably don't actually need to know all state action pairs dynamics models equally well, because if you're never going to visit that state action pair, it doesn't matter if you know it. So we can refine our definition of knownness based on the probability of visiting a state action pair. If you're unlikely to visit a state action pair under the optimal policy, then you just don't need as good of an estimate of it, at least in the episodic case, because it's not going to contribute as much to your value function. When you think of doing the Bellman backup and kind of propagating that information back, you can tolerate worse error bounds on things you're not going to visit very much, because they're lower probability to end up there. That's one thing that we do. The other sort of key insight is that historically, we sort of, in the Bellman backup, you can think of there as being sort of a value function and then this transition dynamics. And you're multiplying the transition dynamics times your discounted sum of future rewards, your value function. And typically, people split these two terms apart and bound each of them separately. And that leads to more looseness. And if we can directly bound these together, then we can end up saving some value. And doing so is not trivial because the samples are not IID. I think that's one of the interesting areas of RL is that your samples are determined by the policy that you're executing. And so we can't always apply standard and concentration inequalities because the samples themselves are correlated.
So the dependence on S, I mean, looks reasonable at first blush, but in most domains you would expect S to be exponential in the natural parameters. So maybe worst case, there's no chance in that. So
yeah, so this is absolutely. So this is still bad. So to go to Dan's point, so if we have the exact same domain, this was 10 to the 12, now we're at 10 to the 6. That's a big improvement, but 10 to the 6 is still crazy, and in general, the state space could be exponential in the number of features. The key idea for this, I'll talk about it, I guess, after the coffee break, but one notion to go with also what Sandra did is to say we're going to restrict the policy class we consider. And so we're going to sort of sacrifice optimality or realizability in some cases in order to get tractability for really large domains.
So the lower bounds for the stationary and non-stationary are the same? So you use the same base, just...
There, yeah, so I think I've got an off by, I think I made a mistake and that should be h squared there, and then this should be h cubed. I'm going to double check that afterwards. So I think I made an error there. On this one, in the bottom case, we're off by a factor of h, h to the fourth versus h third. We think maybe we can get through some of the techniques we used for the first one, get rid of that, but it's kind of subtle. And the lower bound domains that we constructed for the worst case are very different. I mean, they're related, but they're not the same MDP. So I know this is 10:30. I think we get a coffee break now, and then we can continue after.